What I want to start off with today is to remind you, solving trig equations. We've had some steps and we've been gradually building up. The most common and important kind of trig equation is just when you have a trig function equal a number. Twice already. We're using it on practically every problem. I'll just remind you, when we have trig function equal the number, we can always solve it. You just let your favorite letters, such as theta, be the angle in the trig function. This might be some function of x itself. Solve for theta on the unit circle. This might be in terms of inverse trig functions if it's not a special triangle, or if it is a special triangle, then you want to find it exactly in terms of pi. But you solve it on the unit circle, always works. Then put in terms of the original variable x, like theta might be 2x or something. And apply any restriction such as x between 0 and 2 pi. That's how you can solve trig function equals a number, always on the unit circle. Then we said 2, suppose we have a times a trig function plus b equals 0, where a and b are numbers. That's called a linear equation of the trig function. Analogous to linear equation, one variable, ax plus b equals 0. In algebra, you just subtract b and divide by a, and you got an x equals. What you do here, if you have this equation, you subtract b and divide by a and get trig function equal a number. Said minus b over a. Oh, but that's trig function equal a number. So go back to method 1. All right, and then step 3 we said was if you have a times a trig function squared, did some examples of these were harder, plus b times the same trig function, plus c equals 0, we call that a quadratic equation in a trig function, and it's important to put 0 on the right-hand side here. In case you use the quadratic formula, you can put u equal the trig function to get a quadratic equation. AU squared plus BU plus C equals 0, a quadratic equation in U. And solve for U by factoring or the quadratic formula, either way. Factoring is sometimes faster and it generalizes to higher powers if you have more than second power. But the quadratic formula always works. So the quadratic formula, if you want, you just use it on all these test problems where you have a quadratic equation and a trig function. Solve for y by factoring or the quadratic formula. Then you'll get an equation that's either linear in a trig function or trig function equals a number. So you use go to, if you like, method 1 or 2. So that's what we had so far. Start with 3, then you go to 2, then you go to 1, and this thing builds. So we did some examples of that last time. Let's try this example. This is a harder example. Let's say solve exactly, which means I might have to leave it in terms of inverse trig functions. 2 times cosine squared x minus cosine x minus 1 equals 0. Suppose I want to solve exactly this Trig equation. Which method do I use? It's like a cooking class. First, do I bake a cake? Do I bake a pie? Or do I make an ice cream sundae? Go to this one because it's got a square. When you see a trig function squared, I'm going to have to use the one for quadratic equation. These don't have squares in them. So I'm going to say, all right, I'll let u equal the trig function I see, cosine x, to get 2 times u squared minus u minus 1 equals 0. A quadratic equation. Now I see this was a quadratic equation and cosine x. This must be method 3. They aren't labeled like that in the book. I'm just doing this in steps to make it sort of organized. It doesn't call it method 1, 2, and 3. But I get u equals cosine x, and it turns into a quadratic equation. Now, should I factor it? I should use the quadratic formula. I could try factoring first. I have kind of easy numbers. Sometimes factoring doesn't work is the drawback, right? But if it factors, and it factors, it always factors actually. But the trouble is that sometimes you can't guess how it factors, or they might have imaginary numbers in the factors. And when they do, we aren't going to do this. We're only going to do real numbers. So I say it might not factor, it might not factor using real numbers is the point. Blank u plus blank u plus blank. When you can factor it, it always factors this way. And again, a 2 in the first position, I need a 2 and a 1 here. So the product of this times this is 2u squared. And now what has to go in the last blanks, it has to have the product minus 1, right? Remember that, how that works in factoring? Product equals minus 1. Product of these, so that by FOIL you get this, must be 2. Numbers here, and then the u comes out. So I need here 1 and this one minus 1, or here minus 1 and this one 1, if I'm going to guess what goes in the blanks. Let's see, let's try this one. This time this is 2u squared, that's that. Minus 2u plus 1u is minus u. Right? Minus 2u plus 1u is minus u. Oh, that matches. And then minus u minus 1. Sure enough, that's the way it works. So this is equivalent to this. All I did was factor. I'll write it a little cleaner here. 2u plus 1 times u minus 1 equals 0. This is just recopying that. That's what I need in order to solve this equation. Right? But when factoring works, a lot of times you can guess what goes in the blanks really quickly. Now, the zero product property, right? If this product is 0, then either the first factor is 0, this thing, or this other factor is 0. The product is 0, at least one of these is 0. 2u plus 1 equals 0, or u minus 1 equals 0. And then I can put back u equals cosine x. I've got 2 cosine x plus 1 equals 0, or cosine x minus 1 equals 0. And by factoring, I've reduced this to 2 linear equations. So now I can go to method 2, right? A cosine x plus b equals 0, a cosine x plus b equals 0. Method 2 for each of these. But the original equation is equivalent to these 2 equations. And I'm just adding back. Start with method 3. After I factor, I go to method 2 for linear equations and the trig functions. To solve those, right, I just subtract b and divide by a, just like I did in algebra, right? Subtract b, get ax equals minus b. Divide by a, x equals minus b over a. Always works. I'll solve for the trig function that way. Right? So the first one, I subtract 1 and divide by 2. And I get cosine x equals minus a half. And the second one, I add 1 to each side and get cosine x equals 1. I don't even need to divide. So my quadratic equation is equivalent to those two linear equations, or these two linear equations, which are then equivalent to these two trig function equal a number. Now I go to method one. And since I have trig function equals a number, I solve it on the unit circle when I have trig function equals a number. How to make cosine x equals 1/2. I wish this was a theta in here. I'm just trying to follow the notation in the book. Since this is x, I'll call the coordinate on the unit circle x hat and y hat, just to differentiate. So this, I want x hat on the unit circle equal minus a half. This is the line of all points x hat equals minus 1/2, right? It's the vertical line halfway over to -1 here. And I observe there's exactly 2 points on the unit circle where that happens. Hence, 2 terminal rays, there's all that's possible. There's this one. There's this one. And then what angles are they at? And let's do this also. Let's restrict this. Most of the problems do this. Let's solve this only for solutions 0 less than or equal to x less than 2 pi. All right, we're only interested in the direction, maybe not how many rotations. So for the first equation, I'll write it like this. And I notice, since this goes to x equals minus a half, this side of the right triangle here must be plus a half in length. This is 1. This is 1 since it's a unit circle. So these are special triangles. 1/2 1. Square root 3 over 2 has to be the other side by the Pythagorean theorem. And this angle right here must be 60 degrees, pi over 3. We're going to do all these problems in radians for this section just to follow the homework, and I think this is the more important angle system to work in for these problems anyway. And then by symmetry, this one is also pi over 3 because it's also 1/2 by 1 and square root 3 over 2. All right, and if that's the case, then what are the angles in standard position that get to those terminal rays? Well, there's this one here. It's pi, back up pi over 3. So that's one value of the angle x. Or pi, go forward pi over 3. Those are the two solutions on this unit circle. And then cosine x equals 1. Well, again, cosine is the x coordinate. I'll call that x hat on the unit circle, just differentiate from this angle x. And on the unit circle on the x hat, y hat plane, if I want cosine, the x coordinate equal 1, then I want this right here. All right? There's only one point on the unit circle with that x coordinate. So there's only one terminal ray. Right? It's right here. X equals 0. There are your 3 solutions. And then you can simplify them, right? Pi can be written as 3 pi over 3 to get a common denominator with pi over 3. Then subtract the numerators over the common denominator. It's 3 pi minus pi is 2 pi. 3. Here again, if we write this as 3 pi over 3 to get a common denominator, add the numerators. 3 pi and pi is 4 pi. All divided by 3. And then 0. 3 solutions to that problem. Okay, does that look familiar? I hope that's a good review. But then we said not always does it come out to be a nice special angle. And furthermore, there are some other problems that are a little more difficult. I'm going to now add to method 4. There are a few trig equations that come up besides the ones we've already considered. And the most common ones are the following. If more than one trig function occurs, suppose there's a sine and a cosine in there. Or if more than one angle. the same trig function. Try, it doesn't always work, but the common ones you can solve are the ones where you can use a trig identity to reduce it to one trig function. Then you go to method 3 or method 2 or method 1. So use a trig identity to reduce to one trig function. Or once in a while, this other one occurs. It's probably the least likely, but it'll probably be on your test, right? Just try to factor. Put 0 on one side, I guess I should say first. Put 0 on one side. Try to factor with one trig function in each factor. So this is the last one. This is going to put an end to all these new methods, and hopefully in a week you'll be able to do all these problems well. Here's a nice example because it actually employs both those things up there. This is 7C. Suppose I write down sine of 2x minus sine x equals 0. Don't do this on your test. Somebody's going to do this. 2 sine x minus sine x equals 0. What's wrong with that? I use a non-theorem, right? You cannot pull the 2 out of here. This is the sine function of 2x. For brevity, we don't always write these parentheses. We get tired of it, but it is a function of x, right? Even if we don't write the parentheses. So like if you saw square root 2x, you wouldn't just write 2 square root x, right? It's square root 2 square root x. You don't just pull the 2 out. Same thing here. You can't just pull the 2 out. What do you write instead? You know this one actually. The double angle theorem, right? Sine of 2x is 2 sine x cosine x. So don't pull the 2 out. Use the double angle formula. This is what it is equal to. We proved this one, right? Okay, from the sum of difference from the sum formula for sine. So write it there with the double angle formula. This is method 4, right? When you see two different angles, use an identity to get it as one angle. Now it's just the angle x. That's the idea. Method 4, use an identity, get one angle x. Oh, last, but now I've got 2 trig functions. Sine and cosine. How do I get rid of that cosine? Now we'll use the part B here. I see a common factor of sine x in both terms here, right? Remember what terms are? What are terms? It's things that are added together. Factors are things that are multiplied together. In an expression, the factors of the expression are the things that are multiplied together. In a sum of an expression that's a sum, the sums are the terms are the things that are added together. So in each of these terms, there's a sign. I will factor it out. Sine x times 2 cosine x minus 1 is how it factors, right? This times this is this times this is this. There we go. And look, sine is the only trig function in this factor times cosine is the only trig function in this factor, right? Now, if I have 2 factors equal 0, then what do I know about the zero product property? Yeah, at least one of them has to be 0, right? The product is 0, at least one of the factors, sine x or 2 cosine x minus 1 equals 0. There we go. Awesome. Zero product property. So there's the second part, again, method 4. Factor to get one trig function in each factor. Now I can rewrite that by the zero product property. If you want, we can put this in, zero product property. And now what have I got? I've got trig function equals a number and a linear equation of trig function. A trig function plus b equals 0. So I can go to method 2 for that second case and say when I have a times trig function plus b equals 0, I just subtract b and divide by a. The second expression becomes cosine x equals a half. Right? Add 1, divide by 2. Now method 2 has produced two equations, trig function equal a number. I have trig function equal number, method 1, right? I go to the unit circle for each of them. Sine x is the y coordinate of the unit circle, right? So I'll call that y hat so I don't mix up x with x hat with x on the unit circle. X is the angle in the solution here. So this is the x hat, y hat coordinate system. Sine is the y coordinate. I want the y coordinate equal to 0. That's this line, right? Here's the line of all points. Y equals 0. It's the x-axis. Y hat equals 0. That makes 2 points on the unit circle that have that y coordinate. And hence 2 angles. This one, which is this angle, x the angle equals pi. For this one, x the angle equals 0. That's what I got out of this one. X is 0 or pi are the only solutions between 0 and 2 pi. Over here, cosine x equals a half. Well, cosine of the angle is the x coordinate. I'll call it x hat. Right? X is the angle, x hat is the coordinate of the unit circle. So I want all x coordinates equal a half. That's this line here. Half. 2 points on the unit circle have that x coordinate. I construct the terminal rays. Since this goes out to x equals a half here, this side length must be 1/2. This is 1 because it's a unit circle. Tells me that the angle 1/2 something and 1 must be square root 3 over 2, 1 is pi over 3. And correspondingly, by symmetry, this angle is pi over 3, right? We just did the same 1/2 out and 1 over here with a right triangle. So this one had two solutions, x equals 0 and x equals pi. This one, the angle x can be pi over 3, right? But we don't want this one minus pi over 3. We want to take angles between 0 and 2 pi where the instructions. So we'll say it's this angle and say x equals 2 pi back up pi over 3. Which is then 5 pi over 3 if you do the arithmetic. That's hard to see in there. We write the final answer then. Final answer, I got 2 of them here, 1 of them here. No, 2 of them. X equals 0, x equals pi from the first unit circle. X equals pi over 3. You don't have to put them in any particular order. And x equals 5 pi over 3 are the 4 solutions. Here's how you can deal with some of these problems that have more than one trig function or more than one angle. If it's more than one angle, use a trig identity to reduce it. More than one trig function, try and factor or use a trig identity. Get something you can, it's one of the first 3 cases. All right. So they're getting trickier. Those we can solve exactly. Some of these are not so easy, like that. I want to do this one here, one more here. 8b. Suppose I had sine squared x minus 2 cosine squared x equals 0. What method is that? 1, 2, 3, or 4? If I can try and figure it. Like I tell you, what happens on the homework is everybody will do all the homework and think, yeah, I got it. Then you show up for the test and you don't know how to get started because the problems aren't all the same like they were in the homework. They're all mixed up. On the test, you want to, that's why the practice test is out there. On the test, you want to be able to look at it and say, oh, it's this kind of problem, I do this, that kind of problem, I do that. Which of those steps do I do to solve this one? It's not trig function equal number, so it's not method 1. It's not a times the trig function plus b equals 0. It's got squares in here, but it's got 2 different trig functions, so it's not method 3. It must be method 4, right? More than one trig function. What can I do with this? I can either try and factor it, so there's one trig function in each factor, or I can try and use a trig identity to reduce it to one trig function. You see what we do? What should we do? Here's a big hint. Whenever you see a square of a trig function, think of the Pythagorean identity, right? I could substitute for either one of these. Recall the Pythagorean identity, sine squared plus cosine squared equals 1. That tells me by subtracting sine squared that cosine squared can be replaced by 1 minus sine squared. Also, if I prefer, sine squared can be replaced by 1 minus cosine squared. I can use any one of these 3 things to reduce my difficulty in these problems. If I get sine squared plus cosine squared, I'm set. I just put 1, right? But cosine squared could be replaced evidently with 1 minus sine squared, and you need to put parentheses because it all multiplies 2. In fact, let's do that on the next line. So this is equivalently sine squared x minus twice 1 minus sine squared x by the Pythagorean identity. Well, 0. Now there's just one trig function. There we go. Now which method is it? I might try and simplify it a little bit. Sine squared minus a minus 2 sine squared makes 3 sine squared minus 2 equals 0. There it is. How am I going to solve this one? There's multiple ways to solve this, actually. And by the way, you don't have to stick to these 4 steps. These are 4 steps that will work for all the problems here and on the test. But sometimes you'll find a method that's better, and there are other trig equations that can be solved with other methods. They're just not as common. Here's a way I can deal with this one. I can say, oh, this is a quadratic equation. A times sine squared plus b times sine plus c equals 0, where b is 0, right? You can think of this as a. B equals 0. There's nothing multiplying sine, and this is c. It's method 3, a quadratic trig function. Or a quadratic equation of a trig function. So I can actually factor this as follows. I can write it as square root 3 sine x plus square root 2 times square root 3 sine x minus square root 2. Factors like that. That was pretty tricky, huh? It comes out of this formula from algebra that a squared minus b squared factors as a plus b times a minus b. Remember this one? This is a very common factor, a very common formula. If I think of this as a squared, it's square root 3 sine x squared. There's a, right? If I think of this as b squared, b is square root 2. There's b. So it's a plus b, a minus b. That's what I'm doing. Difference of squares factors is a plus b times a minus b. All right, so that was tricky, but it does work, right? It's a quadratic equation on factor. If you don't like this, what can you do instead? Yeah, quadratic formula always works. So you don't have to do it this way. This is just for people who recognize the difference of squares. You can do it immediately, right? Now I subtract, this is method 2. I don't need to write out this step, but method 2. Well, I guess I should, let's write it out. If the product is 0, then either this factor is 0. You don't have to write in quite this many steps. Or this factor is 0. All right, and now it's linear equation. A sine x plus b equals 0. So I'll go to method 2. I'll subtract b and divide by a, and I get sine x equals minus square root 2 over square root 3. Okay? Square root 2/3 if you like. Or sine x here, adding square root 2 and dividing by square root 3 must be square root 2 over square root 3. Two cases. Now I've got trig function equal a number, so it's method 1. But you see how I'm just sort of organizing my thoughts there. I'll say, oh, if it's a trig function plus b equals 0, I subtract b and divide by a. If I get trig function equal a number, I run to the unit circle. Method 1. Sine x equals minus square root 2 over 3. Sine is the y coordinate. I'll call that y hat on this unit circle. Y equals minus 2 square root 2 over 3. It may be down here somewhere. Y equals minus square root 2/3. I'll write it that way. And the second one is y hat equals plus square root 2 over 3. See, that circle will be up near the top. In each case, I observe 2 terminal rays. This one I've got these 2. This one I've got these 2 in order to get the right points of the unit circle. And now I recognize these are not going to be special triangles. This is the tough case, right? On this problem, I should say, this is supposed to be solved in particular on this interval 0 to 2 pi. And it says round to 2 decimal places. Why would it say that? If I say that in the test or you see it in the homework, rounding means it's probably not a special angle, right? If it's a special angle, I can write it in terms of pi and I'm all done. But if I say round, that means it's not going to be a special angle. So, and you can see it right here, right? Y equals square root 2 over 3. If I drop the perpendicular and make a right triangle from here, then this is square root 2/3. That's not a special triangle. Wonder what angle it is. Oh boy, I'm stuck, huh? Well, no, because you have inverse trig functions to solve for those. What is one solution to this equation here? Sine x, which we're solving, sine x equals minus square root 2/3. And then this one we're solving, sine x equals plus square root. What is one answer to this equation immediately? This is a number between plus and minus 1, and this always has a solution, right? One solution is the inverse sine. That'll be one angle whose sine is minus square root 2 over 3. Which one is it on here? Which terminal ray? Arc sine is always between plus and minus pi over 2, first or fourth quadrant. So it's not this one, that's in the third quadrant. It doesn't mean this isn't a solution. It means it's not the arc sine solution. These are both solutions. But the arc sine is between plus and minus pi over 2. So this angle right here is the arc sine of square root 2/3. How about that? minus square root 2 minus the square root. Okay. But that's not even a solution. Why not? Told you these get tricky, huh? This is the trickiest day of the semester, probably. But we'll review these next time. Not a solution because I demand 0 to 2 pi for the interval. This notation means x between 0 and 2 pi. Round bracket means strict inequality, but the square bracket means include the end. So x between 0 and 2 pi possibly equal to 0. And so this is a negative angle. I can't include arcsine. What do I want to use instead? This angle, which is between 0 and 2 pi within one rotation, and this angle between 0 and 2 pi within one rotation. How do I find those? Strangely enough, this angle is pi plus the arcsine of minus square root 2/3. How about that? What? Why would it be added, right? I'm sorry, sine minus. Why would it be subtracted? Don't I want to add it? Don't want to take pi and add arcsine minus 2/3? Why do I subtract it? Tricky questions, huh? Yeah, because it's negative. This is a negative angle. When I subtract a negative angle, then it's positive, it goes counterclockwise. So that's why I subtract a negative angle and it adds, it goes forward. So one solution is pi less the arcsine of negative square root 2/3. What's enough? Well, actually, let's do one more thing. Maybe you remember that arcsine is an odd function, right? Just like a minus comes out of sine, minus comes out of arc cosine. Be careful on cosine. Arc cosine is not even. Cosine is even, arc cosine is not. The inverse function for an even function is not in general even, but the inverse to an odd function is odd. So if arc sine is odd, arc sine is odd. I can pull this minus out and cancel it with this one. I can call it equivalently pi plus the arc sine of plus square root 2/3. That's easier. Well, let's call it that, and I'll just say pi plus the arc sine of plus 2/3. How about that? Because arcsine is odd, I can pull the minus out and cancel it with that one. So this is a better way of writing expression instead of those canceling minuses, right? Those are annoying. Now, what's this one? I can say this one is 2 pi minus the arcsine of minus 2/3, or I can say it's 2 pi minus the arcsine of plus 2/3. I recognize that this angle here is arcsine of plus 2/3, so I can just subtract that. Right? That's the same as this one here. I can subtract that from 2 pi. So that's another. The other angle here is 2 pi less arcsine square root 2/3. Those are the two solutions on this unit circle. Now I got to do the other one, right? What's one solution to this one? I think we figured it out from the first one. Sine of x is square root 2/3. One solution is inverse sine, right? So sine x equals that, then one solution is inverse sine. And where's that? Remember, inverse sine is between plus and minus pi over 2. It can't be this one. It must be this one. All right, it'll always be in quadrant 1 or 4. So here, the arcsine of plus square root 2/3. And that's actually a solution, right? Because it's a positive angle. It has this terminal ray. Then there's one more, this one. By symmetry, this is also the arcsine, right? Because triangles are the same. Which makes this angle pi less that arcsine. There we go. These are the two angles that are solutions to this one. Arc sine, square root 2/3, pi minus the arc sine. Four solutions exactly. Unfortunately, there's more work than this. Because what we asked on this one was round to 2 decimal places. These are, if you're a surveyor or something, your boss doesn't want to come back and say, well, we angled pi plus arc sine. They probably want it in degrees in the first place, but even so, this is nothing. They have to measure it out, right? So what you do is you calculate this on the calculator, and it's actually pretty tricky to calculate on the calculator, these inverse trig functions sometimes, and get them right, because they're complicated, right? So we'll say this is to calculate the first one. To get arc sine, we'll put radians mode, right? Since we're doing this in radians. You want to check your answers in the back. This is what you have to do. You push second sine, because the second button makes it go to the arc sine over the key. And then I need square root 2/3. So I'll push second x squared, because up above the x squared button is the square root. It'll automatically insert a parenthesis, and then I can push 2 divided by 3. And it's a good idea to close your parentheses. If the calculator doesn't close it already, some of them do, then you want to close the square root, inserts a parenthesis here automatically, and close the sign. The reason this is a good idea is that sometimes if you put in the wrong number of parentheses over here, the TI 83 or 84 will automatically close all parentheses when you're done, and you'll think that you have the right answer. But if you would have put your closing parentheses and you accidentally had an extra left parenthesis over here, it would throw an error saying, no, you can't do that. So this actually helps you catch errors if you close those. If you have the wrong number of left parentheses, this will catch it, maybe. So I'll say suggest that and then push enter. And what you should see in your screen is arc sine, parenthesis, square root of parenthesis, 2/3 for 2 divided by 3, close, close. This should appear on the screens. Arc sine of square root of 2/3. There we go. Oh, and I need plus pi, so I forgot my plus pi here. Plus second caret has the pi over it. We'll carry pi to lots of digits. Now I'll push enter. So plus pi. Now let's see what that comes out to be. I think what is easiest, you just try and do those out by heart and then look on the screen and see if it says that, right? Hopefully it does. Inverse sine. Show some radians mode real quick. It is inverse sine, square root by 3, parenthesis, plus pi. Okay. What do I get here? Looks like I'm going to get 4.0969, blah, blah, blah. Round to 2 decimal places means 2 places after the decimal point. It's not 2 significant digits. It's going to be 3 significant digits. Since this next one is 5 or greater, you round this up and call it 4.10. And that's your answer. You carry the 0 to show that that digit was significant. Then we can do the others similarly. 2 times this arc sine, square root 5.33. To work these similarly, you should get that. Arc sine of 2/3, I should have done that separately. Arc sine to square root of 2/3. .96. And pi minus that, 2.19. If you try the homework, hopefully you get those. Questions on that one? Somebody get pretty long, don't they? Well, that's all the methods now. You guys can be experts in this stuff. Just have to practice a bunch of these. As you can see, a lot of it just comes from sort of recognizing what to do. When you see a sine squared in there, think, oh, maybe I can use the Pythagorean theorem and get cosine squared and make one trig function, right? Kind of thing. Well, I want to point out one pitfall in here. This is 7g. This minus 3 sine t equals 15 cosine t sine t. Let's solve this exactly over the interval 0 to 2 pi again. How am I going to do that? I see a sine, I'll just divide through it and write it as minus 3 equals 15 cosine t. Now I've got it, right? I made a mistake already. What's wrong? Just have to be careful when you multiply through or divide through by a trig function. What can happen is this. Suppose I had the equation x squared equals x. There's two solutions, x equals 1 and x equals 0, right? What if I divide both sides by x, right? Then I have x equals 1. I just lost one of my solutions. What's wrong? Why can't I divide both sides by x? Divide both sides by any non-zero number. So when I divided, I assumed this wasn't 0. I have to check x equals 0 separately. And x equals 0 is a solution. So this is equivalent to these, right? The same thing can happen here. When you divide by a trig function, you can lose some solutions, right? Just the same way. When I divided through by sine t, I assumed sine t wasn't 0, but sine t equals 0 is a solution, right? So if I put also sine t equals 0, then these two are equivalent. So you can do that if you want. This is not one of my 4 steps here, but you can do this if you want. I just wanted to point out. You can say, well, divide by sine t and then check sine t equals 0 separately, and it is a solution. 0 equals 0 results. However, you don't ever have to do that if you just follow the 4-step method, right? What you do with the 4-step method is when you see more than one trig function, you put it equal to 0. That was method 4. Get 0 on one side. So I'll add these over and get 0 equals 15 cosine t sine t plus 3 sine t. Adding 3 sine t each side. Now I might divide that by 3. That's a non-zero number, so I can divide through by 3 with no worries of losing any solutions. I get 5 cosine t sine t plus sine t. So divide by 3, that's algebra. And now, how do I solve that one? Now that I have 0 on one side. It's more than one trig function, method 4. So I can either try and use a trig identity to reduce that. Well, I could write sine times cosine as 1/2 sine of 2x, but then I get 2 angles. Or I can try and factor it with one trig function each factor. I see a common factor of sine in here. So instead of doing that trick of dividing through by sine and checking sine equals 0 separately, you can factor out sine here and avoid that dilemma. Find 5 cosine t plus 1. This times this is this expression by factoring. And now sine is the only trig function in this factor. Cosine is the only trig function in this factor. This is equivalent by the zero product property to sine t equals 0, or 5 cosine t plus 1 equals 0, right? So there's an equivalent statement to this one. Now I've got a linear expression, so I go to method 2, right? The first one stays the same. I don't need to do anything yet. This one, I subtract 1 and divide by 5, and I get cosine t equals minus a fifth. Right? Now it's trig function equals a number, trig function equals a number. I go to method 1, solve it on the unit circle. And in this case, this one does come from a special angle, but this one doesn't, right? So the first one, if I solve sine t equals 0, trig function equals a number on the unit circle. Sine is the y coordinate, so I'll put y equals 0. That's this line right here, which corresponds to this terminal ray or this terminal ray. T equals 0 or t equals pi are the possible solutions to this one. The second one is cosine t equals 1/5. Cosine is the x coordinate, x and y. So I have 1/5 of the way over here, x equals 1/5. Tells me there's 2 terminal rays here. That's it. So within 0 to 2 pi, I only have 2 solutions. What are they? Unfortunately, right, it's not a special triangle this time. This length is 1/5, since it goes from 0 to 1/5. This one is 1. I can figure this with the Pythagorean theorem, but I don't need it. I need this angle. What is this angle? Got to get it this time. What is that angle? Yeah, it's arc cosine, right? Cosine in this triangle, cosine of angle T is 1/5. So this is the arc cosine of 1/5. Plus one solution to cosine equals a number between plus and minus 1. It's always the arc cosine. So T equals arc cosine of 1/5 is one solution. Well, wait a minute, is it this angle or this angle? How do I know?
Shouldn't it be negative?
Oh, did I mess it up? Yeah, I miscopied. It was minus a fifth. Thank you. Wrong answer. Yeah, minus a fifth. This angle and this angle. And now this one will be the arc cosine of minus a fifth. Because the arc cosine is an angle between 0 and pi, first or second quadrant. It won't be this one. Now, if that's arc cosine of minus a fifth, what's my other angle? This one. That. So you have to practice these, they get tricky. But if you draw the picture, it really helps. Well, by symmetry, this one is the same as this one, right? So this is also arc cosine. It's a fifth. So this angle is 2 pi, back up that arc cosine. So my solutions from here are arc cosine, negative a fifth, 2 pi, less that arc cosine. Be careful, don't try and say it's even and take away the minus, right? The inverse of an even function is not even in general. Right, inverse of an odd function is odd, you can pull it out, but don't do that with even functions. Right. So those are the 2 solutions there. And then over here, we can find them exactly, 0 and pi. Right. Those are the 4 solutions. Now, if I ask you for exact solutions, this is it. You finish right here. It's considered an exact solution when you leave it in terms of inverse trig functions. Right? However, on 8, if this is part of 8, this is 7. On 8, it asks you to give the decimal number. And if you're a surveyor or something, somebody architect, you may want to be measuring angles, then you would put this in degrees probably and actually calculate it out. But for a mathematician, you want to leave it there so you can come back anytime later and get as many digits as you need from this exact answer. Exact solutions. Okay. So quite an array of problems can come out from here. Well, there's another interesting one here that can come up. You should see. This is now. It's this one. Let's see. Yeah, let's call this. This is 4D. Suppose I had 4 sine squared x equals 3 plus 4 sine x. Find the solutions to that one. First, now let's put it equal to 0. 4 sine squared x minus 4 sine x minus 3 equals 0. Now, what kind of equation is it? A sine squared plus b sine plus c equals 0. It's a quadratic equation in sine. So for that, method 3, I put 4u squared minus 4u minus 3 equals 0 with u equals sine x. From the quadratic equation, I can try factoring or the quadratic formula. Which would be better? This is tricky. Here's a hint that we haven't talked about before. When you want to guess what goes in the blanks, it has to be guessable. This can have terrible, complicated things that go in the blanks. If you're going to get whole numbers in the blanks, what you need is the discriminant b squared minus 4ac to be a perfect square. What happens is that b squared, on these things, a u squared plus bu plus c equals 0. If b squared minus 4ac is greater than 0, what do you know? Immediately, just from that. The quadratic formula is going to predict there's 2 solutions, right? Because you get a square root of that number and get one solution for plus and one solution for minus, right? If I apply the quadratic formula, this, it's going to say u equals minus b is 4 plus or minus square root b squared minus 4 times a times c. Well, I'll go ahead and finish this. It's not the one I thought it was. I was looking for this one. We'll do it. Go ahead and do it. 4ac and all over 2a. So it looks like that. And what do I get? 4 plus or minus. See, 16 plus 48 makes 64. So I get square root 64 all over 8. And my solutions will be 4 plus or minus 8 all over 8. Or let's see, 12 eighths is 3 halves. And minus 4 eighths is minus 1 half. So there's the solutions by the quadratic formula. So if I see b squared minus 4ac is greater than 0, in fact, it's 64 in this case, then I know I'll get one solution for the plus and one solution for the minus. So bear in mind, this will always mean 2 solutions. And then if b squared minus 4ac is equal to 0, then it'll be plus or minus 0 here. You get one real solution. Two real number solutions. But if b squared minus 4ac is negative, the quadratic formula will get a square root of a negative, and you'll find out there's no real solutions. There are actually solutions with imaginary parts that can work in there, but we're not interested in imaginary solutions, right? There's no real solution. This is positive, we can do that. And here's an interesting result. When this comes out to be a perfect square, like this is b squared minus 40c equals 64, right? We can calculate this out. When it's a perfect square, you could have factored it also. So we also could have factored, and it would have worked just as well. All right, so now I've got 3/2 and minus 1/2. I'll break this up into two parts. And say, evidently, you with sine x equals 3/2, or sine x equals minus 1/2. So this equation, you have to put 0 on one side to start, otherwise the quadratic formula won't work. With 0 on one side, you can apply the quadratic formula and get 3/2 and minus 1/2 for sine x. Now this is trig function equal to a number. You go to method 1. You solve each of these on the unit circle. Now the first one has no solutions. How do I know that without even drawing the unit circle? I'll draw it to illustrate. Sine is always a number between plus and minus 1. This is greater than 1. There's no solution. You don't even need to sketch the unit circle, but if you do, you'll say, oh, this is the y coordinate. So I want y hat equals 3/2. It's right up here. It doesn't intersect the unit circle, so there's no solutions, right? So you draw it, you'll see it, but even without drawing it, you can't get sine equal to a number bigger than 1 or less than minus 1 will be down here. No intersections, no solutions. However, this one, the number is between plus and minus 1. It will have solutions. This is the y coordinate, y hat equals minus 1/2. It looks like that. This one will have solutions, and in fact, there'll be a special triangle at this case. Because if I come down here, through those points on the unit circle that have that y coordinate, and drop the perpendicular, since I went down to y equals minus 1/2, this side is 1/2, and this is 1. So it's a 30, 60, 90 triangle. This is pi over 6. And this is pi over 6 by symmetry. The two angles I want here are pi plus pi over 6 is 7 pi over 6. And instead of minus pi over 6, I'll go around this way and say it's 2 pi less pi over 6 is 11 pi over 6. Writing kind of small there, sorry. 7 pi over 6 and 11 pi over 6. And this one has no solutions. So these are the only two solutions. This means empty set in mathematics. Okay. So you have that kind of thing that sometimes you get sine equal to a number that's too big or too small, a trig function. It has no solution. And then one more case. Suppose I had tangent squared x plus tangent x plus 2 equals 0. What are the solutions to that one? How would I solve that one? Well, it's not trig function equal to number, so it's not just method 1. It's not linear. It has a sine tangent squared, so it's not method 2. Method 3, it's a times tangent squared plus b times tangent plus c equals 0. I can use method 3, right? And say, oh, substitute u equals tangent x. to make it a quadratic equation, right? U squared plus U plus 2 equals 0. Plus with success of like U by the quadratic formula, which always works, is minus B plus or minus square root B squared minus 4 times A times C all over 2A. Minus 1 plus or minus square root -7 all over 2. Well, square root of -7, what's that? Yeah, there's no solutions. So if you get a square root and a negative doing that, done. All right, well, that pretty well covers it. I thought about starting the next section, but I think I'll just, as we go. That's left. Let me just do one more review problem here. Just briefly last time, actually, but. Here. Was this one, 8A. Suppose I have tangent squared x plus 3 tangent x minus 3 equals 0. When you try this one, it's kind of tricky. Right? That's a quadratic equation in a trig function, so I rewrite equivalent with u equals tangent x. Again, method 3 if you like. To make it a quadratic equation, u squared plus 3u minus 3 equals 0. Again, I can try the quadratic formula and say u equals minus 3, that's b, minus b, plus or minus square root. B squared is 3 squared minus 4 times a times c, all over 2a. Minus 3 plus or minus square root of 21 all over 2. Minus 3 plus or minus square root of 21, what do I do with that? Still trig function equal to number, right? Two different numbers. So it's actually method 1. You've got trig function equal to number. Tangent x can be the first number, minus 3 plus square root of 21 over 2. Or it can be the second number, minus 3 minus square root of 21 over 2. How about that? So you just have to apply this method 1 twice. And now, what's one solution to this? So, this means solving on the unit circle. Trig function equal to number. What's one solution to this? Does it have a solution? Maybe it's like sine, it doesn't have a solution. How do I know? Sine equals a number and cosine equals a number only has a solution if the number is between plus and minus 1. But tangent equals a number always has a solution, right? Tangent is this function here. It looks like this, and then it repeats, has asymptotes, right? But if you tell me 100, there is an x for which tangent is equal to 100. If you tell me a googol, 10 to the 100th power, there's a solution for which tangent x is equal to a googol. It doesn't matter what you give it, what number you put here, tangent always has a solution. And what is one solution? You know what? What's one solution to tangent x equals that? Yeah, arctangent. There we go. Arctangent. Even though it's a messy number, it is a solution. Minus 3 plus square root 21 all over 2. That's one solution. Now, I can roughly sketch it here. Square root 21 is bigger than 3, right? Square root of 9 is 3. In fact, this is bigger than 4, but it's certainly bigger than 3, right? And so I got -3 plus the number bigger than 3 makes the top positive. And the bottom's positive, so the whole quotient is positive. Tangent is positive in quadrants 1 and 3. So I don't know exactly where this angle is, the arctangent. Maybe it's here, right? Or maybe it's here. What happens when you have tangent equal to a number is the two opposite angles are always both solutions, and one of them is this. One of them is the arctangent. Which one is it? Arctangent is a number between plus and minus pi over 2, right? Quadrants 1 or 4, it's this one. So that's one solution. Arctangent of -3 plus square root 21 over 2. What's this other solution? The opposite direction is always also a solution. It is, yeah, it's the opposite direction. So you just add a straight angle pi. Awesome, yeah. Pi plus the arctangent. -3 plus square root 21 over 2. You can run those on your calculator. On 8, it says run on the calculator to get the numbers. We don't have time for that. We're almost out of time. But this is the solution. This is the solution. And now what about over here? This is tricky too. Let me get a little more room. Because there's two more solutions that aren't on your answer page, actually. What's one solution to this one? Arctangent equals this one. Well, you got the last one. Tangent can be any number. One solution is, yeah, arctangent. -3 minus square root 21 over 2. Now, this is a negative, right? A negative minus another number is negative. Over a positive is still negative. So a tangent of giving negative is going to be in quadrant 2 or 4. So there's going to be an angle somewhere in here. I don't know exactly where it goes. I don't have to be exact. And the opposite one are both going to be solutions to this. Which one is the arctangent? Is it this one? Is it this one? Is it this one or this one? Arctangent is between plus and minus pi over 2. It's this one. What we want is not that one, though. We want the angles between 0 and 2 pi. So we want this one and this one. What are our solutions here to the last part? These two are solutions here. This is a solution. This is a solution. You can run in your calculator. It asks you for decimal. This one is not a solution. You have to calculate. This is a negative angle, right? Because it's clockwise. So this angle here is actually 2 pi plus this negative angle, right? It's 2 pi plus arctangent -3 minus square root 21 all over 2. Plus, because this is a negative angle, it'll take us back clockwise, so you don't subtract it. And then this one here, what's this one? Well, by symmetry, this is the same angle, right? If this is arctangent, this is also arctangent. And I can take pi plus this negative angle. There it is. Maybe the hardest problem in the course, I don't know. Two more solutions. 2 pi plus this arctangent and pi plus this arctangent are the other two. These are not listed on the answer key. You're supposed to run the decimal of that. We're out of time, so I'll just leave it right there. But there's 4 answers to this one, not 2 is listed in the key. See, we have a hard time with this one too. So, all right, bring some questions next time. We'll go over and